Hello, everybody. Thank you for joining this presentation of LioniX International. During the Photonic Plus event, I want to tell you something more about LioniX International and give you some flavor of highlights of application models that can be made with our Photonic Integrated Circuit technology. My name is Arno Lijnse. I'm the CEO of LioniX International. And I hope to tell you more and show you nice examples in the next 8 minutes. So LioniX International is a vertically integrated foundry, and that's also what distinguishes from other pure-play foundries. We build customized solutions for OEM customers based on our tool set, which originates from customized MEMS, micro-fluidics, and in particularly also integrated photonics. We built at the forefront of technology development new applications for customers from prototype to volume production. Our unique selling point in the technology is our low-loss silicon-nitide based waveguide technology, which is branded TriPleX, and that operates from 4 or 5 nanometers to 2.35 microns. Nice thing of the waveguide technology, which is inherently a passive technology, so we can do phase shifting and tuning at kilohertz, megahertz range, but we cannot do generation of light or the ultra fast modulation. The nice thing is, what we can do is adapt the mode profile so that it matches the active platform, so it matches fiber. And therefore, you can put functionality where it fits best, have low loss fiber chip coupling, have low loss coupling to active platforms, and really be an intermediate platform with functionality where you put the functionality where it fits best. So a low loss functionality with long delay lines or filtering or data processing in the silicon-nitide platform and the active components in the rest. These active components are combined now with hybrid assembly, so end-fast coupling, flip chip coupling of components on chip. And in the coming slides, I want to show you some examples of our technology and what the technology can do. So I'll start at the visible light, and on the left side here, you see a module which we've made for one of our customers where we had to create a very well-defined interference pattern. This one is used for DNA sequencing. And the goal there was to have a relatively high power light source, about 300 milliwatts, very uniformly defined, creating interference patterns where you wanted a few percent accuracy over the device. The fact that these light sources or the ports had to be so close together for bulk optics, that would be very difficult. In integrated photonics, the nice thing is that it's relatively easy to combine. Because once you're on a chip, the world is your oyster. You can vary, you can design and play around within the boundary condition of the lithography, of course, but you can have a lot of design freedom there. Moving a bit in the wavelength range, going to visible and 850. On the right side, you see our biophotonic sensing platform, where in the middle with the red light propagation, you see an example of our biophotonic sensing chip. And this is a development which we're currently doing with our partners Servix and Curing Diagnostics, and it's supported by the Dutch Photon Delta initiative. And with these biosensors, which are based on evanescent field sensing and proper surface functionalization and biochemistry on top, which makes the chip selective, you can do very sensitive detection. And these sensors are currently used for early cancer diagnostics, but also for COVID-19 sensing and a variety of other applications. The nice thing of these modules is that you can see it right here. I got my mouse pointer here. You see a small spot. Once you're on chip, you can also integrate easily grading couplers where we can flip chip VCSELs and detectors on top, and in that way create a fully disposable sensor where the chip footprint is really small and it becomes a cost-effective disposable sensor that has a very high sensitivity. We move a bit into the infrared range. We see particularly for microwave photonics and 5G, 6G, but also for optical beamforming networks in satellite dishes or in antennas on top of airplanes. We see that photonics starts playing a role there in really the microwave photonics, the handling of RF signals in the photonic domain. On the left picture, you see examples of modules where we have what we call an optical beamforming network. So we transfer electrical signals from an antenna to the optical domain, do the processing of those, we delay the signals and coherently combine them again, send them to a detector, and then the output of that is again RF signal, and it becomes a module which is RF in, RF out. It can be used in these kind of phased array antenna systems. For these systems, what is required is a very high power, accurate light source. And either in some years ago, we could decide to buy them, or we could say, you know what, once we're on chip anyhow already, can't we make the laser ourselves? So what we did was we take an external cavity and we take a gain medium, in this case it was indium phosphide. If you combine those, you can build very low loss cavities, which are tunable, wavelength selective, and in that way we can create very narrow line with lasers, with also very high power. Current ones are well over 100 milliwatts, very narrow line within the kilohertz range, fully tunable over the band of that gain section. In this case, is a C band, but they're also open in other wavelength ranges. And very sharp wavelengths and very high side mode suppression ranges of better than 50 dB and even 60 dB. You see now that these lasers also become more and more interesting for sensing applications. And a hybrid combination of silicon nitride, in this case indium phosphide, enables that. Moving back again in the wavelength range to the visible and to the also 1550 in this case. The narrow line with lasers and the quantum computers. And the building blocks which I just presented for microwave photonics, these same building blocks and the same integration technology can also be used for quantum computing. And on the left side, you see an example of a module which is currently being used by PICs for quantum computing. And they're currently making 4x4 or 12x12 modules, which can be used fully configurable for quantum computing. And actually, that's the state of the art now. World record leading in creating these kind of large matrices, and upscaling to even larger matrices is targeted for later this year. It's a fully turnkey system, which you see over here. Oh, there's my mouse pointer over here. For instance, is a full box which with a computer can be driven, and you can select and drive the matrix by software. On the right side, and I already mentioned earlier, the lasers that we work on work at 1550, but we also made them at visible light, and the complete wavelength range actually from 4.5 to 2.35 microns is enabled with silicon nitride. The moment you have a gain section that can generate the photons, you can create an external cavity to create a very narrow line with laser. The picture you see here is one from Red, which was published at Photonic West last year, and really showing kilohertz line width lasers in the, this case, red propagation region, 680 nanometers, if I'm correct by heart. But that full visible range can be covered in this, which also opens up new applications in sensing and in competences. The nice thing is, because you have it in the package, it's very robust, it's integrated, it's fixed in the package, you don't have to calibrate or retune things. These modules were even vibration tested, and the nice thing is you count, they passed, what was it by heart, about 40 G RMS, which is 120 GP. And that's a nice thing of integrating chips in such a way they're very small and they're rigidly combined together. So you can build rigid, compact, and robust, stable devices. Some more visible light examples just to trigger some thoughts in your head. You don't have to stay on chip. For instance, what we do on the left picture, the lower left, is that we create, by focused ion beam milling or by gratings, we create outcoupling mirrors where indeed wavelength dependent you can outcouple, or you can use a multiple of these. And you see that in the picture in the top right, where we created an array of these to create different shapes of interference patterns. And by playing then with the phase and switching the light on chip, you can really control the interference patterns that you're making. And you can therefore, without moving parts, create these interference patterns. The integration of these light sources is shown in the lower right picture. And as I mentioned earlier already, we can do flip chipping of these VCSELs, and the hybrid combination of these components enables these kind of new applications. Staying in a visible range, and these are always nice examples to show it, because visible light you can see, that makes life much easier, and also that brings in new applications which are the non-standard integrated photonics. Everybody knows integrated photonics from the telecom, of course, but you see now and now that silicon nitride becomes more and more important. That also visible light applications like AR, VR, the VR glasses or the AR glasses in this picture, for instance, is a module which is created by North in their developments. And these kind of modules, the AR, VR modules of the future, will require more and more integrated photonics also. An example which we show here is that you can create red, green, blue easily on a chip, integrate attenuators on the chip, that you can switch the different colors, that you can attenuate them, that you can control basically the color there easily without having to have all sorts of bulk components which you have to assemble and align. In this case, you integrate the different components on a chip, and you got really red, green, blue module where the light is coming out of a single mode waveguide. All colors are combined into that single mode waveguide. This actually was my last slide to show some highlights, and it was not my intention in 8 or 9 minutes to teach you everything about integrated photonics, but just to plant a seed of what photonics could do for you. So in case you want to discuss with us whether the technology or the modules could be suitable for your application, please don't hesitate to reach out to us. Visit our website, check our, send us an email with your request. We're open to discuss with you what we can and what we cannot do. Thank you very much, and looking forward to hearing from you.